In the last unit, we learned how to prove partial correctness of a while loop. And in this unit, we're learning to show that the while loop terminates so that it is actually true. So the first thing we need to do is to figure out a bound function to show termination. We usually refer to that bound function as t. And it is a function of something that's happening consistently in the loop. Well, notice that there are two things that are changing in the loop. ck is changing and k is changing. ck is just the sum of the entries in A and B. I'm not sure if they're positive or negative, so I don't know how to compare ck and ck plus 1. But k becomes k plus 1, and I do know that that's always increasing. So I think that the function I'm looking for is going to be a function of k, and this is typically the case. The bound function is often a function of the increment. In this case, that's k. And so the other thing, though, is we want this bound function to be decreasing, and k is increasing, but minus k is decreasing. We also want it to be bounded by 0. And notice the guard, or while we're iterating, it's bounded by 0. The guard is that k is less than n. And if k is less than n, we could rewrite that as n minus k is greater than 0, which means to me that this is the function I'm looking for, that the bound function should be defined to be n minus k, because it is decreasing because it's minus k, and it is bounded below by 0. So now we would need to show that this is true. How do we do that? Two more steps. We need to show that while we're iterating, and we're iterating when the invariant holds and the guard holds, that implies that this bound function is greater than or equal to 0. Secondly, we need to show that it's decreasing, which is a little bit harder. While we're iterating, which means that the invariant and the guard have to be true, but we need to compare to show that it's decreasing. And so we need to make a copy. Let t prime be the copy of t. Then we're going to perform the commands inside of the while loop. And after, if we compare the t that was copied to the t after, the copy is larger. So these are the two steps that we need to show for showing that it does terminate. Why? Because if we have a function that's bounded below, say by 0, and we know every iteration it's decreasing, eventually it had to have stopped, because these two things can't happen infinitely often unless the amount that it's decreasing goes to 0, and that's not the case in these kind of problems. They're actually decreasing by a chunk. And so these two predicates holding means we terminated, because they can't both be true infinitely often. So in the next videos, what I will do is to show that this particular code segment does terminate.